Okay, next we have energy stored in an electric field. By definition of the capacitor, from the definition of the capacitor, we say that a capacitor basically stored electrical energy. Like how we can define a capacitor: a device which stored electrical energy is called electrical energy or electrical charge, or electrical charge is called capacitor. How it can store an electrical energy? First I will explain the concept which we will already discuss before. Suppose we have charges which are situated at infinite distance from each other. Now if we bring these charges close to each other, like this charge which I move from here to this point, this charge I move from here to this point, and this charge I move from here to this point, then what will happen? We need to do work to assemble these charges, and that work can be stored in the form of potential energy. This is the concept which we already discussed before. Now suppose we have two charges. Let's suppose two charges, one is plus q and the other one is minus q, which are close to each other. If I separate these two charges away from each other, we are doing work, and this work is stored in the form of potential energy. Now how to get this energy back? We have to release these two charges. Once we release these two charges, they come close to each other again, and they release energy in the form of kinetic energy. Now in charging a capacitor, what will happen? Suppose we have a capacitor which is connected to an external battery with potential V. What the role of this battery? This battery pull charges from this plate of the capacitor, electron from this plate of the capacitor, pull electron from this plate of the capacitor, and induce those charge or produce those charge on this plate. So electrons goes from these plates, so we have positive charge here, and electrons are stored on this plate, so we have negative charge on this one. So it means that this battery is doing work in moving charge from this plate to this plate. Once charges are separated, positive charges appear on this plate, negative charges appear on this plate, then we have electric field here in between these two spaces. So it means that the work which is done by this battery by consuming its chemical potential, chemical energy, to bring charge from this plate to this plate, this work done can be stored in the form of potential energy in the space between this capacitor. We can say that for charging a capacitor, work must be done. Due to this work, an electron transfer from one plate to another plate, like from this plate to this plate. In this way, an electric field is set up between these two plates of the capacitor, and the work which is done by this battery by consuming chemical energy is stored in the form of potential energy between the space between the plates of the capacitor. So this is the concept behind energy stored in an electric field. Now suppose that at time t, suppose that initially we have time t, a charge q has already been transferred. Like at time t, charge q is q prime. Let's suppose q prime charge is transferred at time t. Charge q prime is transferred from one plate to another plate. Due to this transfer of this charge q prime from one plate to another plate, a potential difference is developed across these plates, which I call V prime, which is equal to q prime over C, because we know that C is equal to QV. So from this we can get that V is equal to C over Q over C. Let's say this is equation number 1. Now what will happen? After time t plus dt, suppose an increment of charge dq prime is now transferred. Like at time t, there was a transfer of q prime charge from one plate to another plate. Due to that transfer of that charge, what will happen? Potential difference appear across the plate, which is given by this relation. Now after time t plus dt, an increment of charge dq prime is now transferred from this plate to this plate. So the total charge per transfer is now q prime plus dq prime. Now due to the transfer of this increment of charge, electric potential energy stored will be du, which is equal to V prime dq prime. Because we have the definition of electrical potential is equal to electric potential energy per unit charge. So electrical potential del V is equal to del U over Q. From this I can get del U is equal to del V into Q. So this is from this relation. Now using equation, I call it equation number 2. So using equation 1 and 2, we have du is equal to, instead of V prime I put Q prime over C into dq prime. Now this is a small increment of charge transfer from this plate to this plate. If I say that the total charge is transferred, like the total charge Q is transferred from this plate to this plate, then the total potential energy stored in the capacitor is du, which is equal to Q prime over C dq prime. But the charge stored, initially there was zero charge transfer, and finally the total charge is transferred from this plate to this plate. So we start transferring of charge from 0 to Q. So from this side we get U, which is equal to integral from 0 to Q, and we have 1 over C is constant, so I can keep it outside of the integral. We have Q prime dq prime. Now integrate this equation, we get 1 over C and 1 over 2 Q prime square, and the limits of the integral are 0 from Q. So this is equal to 1 over C into 1 over 2 Q square. Or we can say that this is equal to Q over 2 Q square over 2 C. This is the potential energy stored. Now we also know that Q is equal to CV, so U is equal to, instead of Q square, this is capital U. We have C square V square over 2 C. C cancel with this C. So we have U, which is equal to 1 over 2 CV square. This is the potential energy stored in the capacitor in terms of capacitance and potential difference. Now next we have to calculate the potential electrical energy density. So for electrical energy density, we define the electrical energy density as electrical energy density. We can define electrical energy density, which I represent by this small u, which is equal to electrical energy per unit volume. Now suppose we have a parallel plate capacitor. This has a separation D, and let's suppose it is an area A, then the volume of this region in between the plate of the capacitor is AD, which is volume. So energy density, electrical energy density will be equal to U over AD. Now we know that U is equal to 1 over 2 CV square. So the energy density will be equal to 1 over 2 CV square over AD. I can say that U is equal to electrical energy density. So we have to differentiate between electrical energy density and electrical potential energy. This is the symbol for the energy density, and this is for the potential energy. So we have this, which is equal to 1 over 2 CV square over AD. Now for parallel plate capacitor, the capacitance is given by C is equal to epsilon naught A over D. So using this value here, we get energy density, which is equal to 1 over 2 epsilon naught A over D into V square over AD. A cancel with this one, so we have the energy density U, which is equal to epsilon naught over 2, and we have V square over D square. And we know that electric field is equal to electric potential over D, V over D. So instead of this, I replace it by U, which is equal to 1 over 2 epsilon naught E square. Now this is the energy density in terms of electric field. Now we derive this relation for a specific case by using a parallel plate capacitor, but this result is also hold for any kind of capacitor, whether it is a cylindrical capacitor, or it's a parallel plate capacitor, or a spherical capacitor. And we also assume that the medium between the plates, or between the cylinders, or between the sphere is air. Now if the medium between the plates is other than air, like some insulating material, then we have this relation, which is equal to 1 over 2 epsilon E square, where epsilon is the permittivity of medium. So this is all about electrical energy stored in an electric field.